So we have satisfied, so we have finished analyzing the slenderness ratio for LE XY over RZ. Next, we're going to find along the exact plane. So now I'm going to sketch out the exact plane, and I'm going to do it side by side so we can see it clearly. Yeah, I'm going to draw them in side by side. So now we are going to view in the so we are viewing the XY plane. Now we are going to view in the exact plane. Okay. So exact plane. So this is my Z. And over here is my X. And then we are going to rotate about Y. So something changed over here. The fixing. Okay, I'm not using the right term, but how the ends are fixed are different now. Okay, and I'll show you why. So this is our structure. At point B now, this is still what? This is still built in, where M is not equal to 0. Okay. Whereas the other side, if I were to sketch the centroid, and then we have this part over here. Okay, we have the beam over here. Okay. So where I draw the sketching line is I draw the sketching line of this. Okay. However, it did not restrict the degree of freedom or of deformation. Okay. So if now I were to sketch the centroid, and now if I were to sketch the centroid now, right? Now the buckling, and then again, we have a load P coming from the top. Now buckling will occur in this direction now. Right? Why it bends this way? Because we did not restrict the Z direction motion. Okay, we did not restrict the Z direction motion. That's why the deformation has gone this way. So if you when you look at the location at point A now, right? We know that the moment is equal to 0, right? And we know that X and Y are also equal to 0. Okay, so the other end is like free. Okay, so if we go back to here, one end fixed, one end free. Okay, so with reference to this figure over here, I'm going to hopefully I could do this. Yes, I could. And I'm going to shift this slightly over so there's space. And you can see for yourself, right? One end is fixed, the other end is free. So for this case, our LE, I'll write this down, our LE on XY plane is equal to 2L. Okay, is equal to 2L. And the rotation, right? The rotation is about YY axis. Okay, the radius of curvature. So the curvature of this and the curvature of this, right? Of the arrow over here has the same like curvature. Okay, if I have to draw, probably you don't see it yet. Let me sketch. So this is our rotation about Y. The curvature and this curvature is the same orientation. So for this case, we know we have to use IYY. Okay, so we note that IYY is equal to A RY squared, the radius of gyration squared. So we also know that RY is equal to square root of IYY over A. So next we have to determine what is our IYY. Okay. So again, I'm going to use the same image over here. We're going to look at the plan view. we're going to look at the plan view over here. It's okay. I think I'll just sketch in another one. Right. So this is our Y. This is our Z. Okay. So now we are going to focus on YY. So when that's the case, this will be our width. And over here, the perpendicular distance. Okay. Perpendicular distance over here. This is our depth. Okay. So we know that this dimension over here is our B. This dimension over here is our A. So we can now formulate our IYY. So IYY is equal to the width, which is B, which is A. Then our depth is B cubed over 12. Okay. So now if we were to calculate what is our RY, so RY is equal to square root of IYY is AB cubed over 12. Divide by the cross-sectional area, which is AB. So this will be equal to B square root of B squared over 12, or is equal to B over square root 12. Okay. So now we are going to formulate, or we are going to put them, we're going to equate both equations, or we're going to satisfy this equation over here. Okay, I'm going to go into the next page. So we have LE. I'm going to copy the whole thing. Okay, so we're going to put in our values. So LE XY, okay, so it's 0.7 L divided by RZ. So our RZ, which we have found over here, our RZ is A over square root 12. And this whole thing will be LE XZ. So our LE XZ is equal to 2L, right? And this is equal to B over square root 12. Okay. So now we can cancel our L's. We can cancel our square root 12. Okay. So A over B. So we now have worked out our ratio now. So A over B is equal to 0.7 divided by 2. Right? So therefore, the A over B ratio is equal to 0.35. Or A is equal to 0.35 B. Okay, so this is the relationship that we have, such that we satisfy the optimum design of the structure, okay, such that the slenderness ratio in the XY plane is the same as XZ plane. Okay. So what this means is the buckling, the sensitivity of buckling, okay, in the XY plane or on the XY plane over here is as sensitive, okay, as in the XZ plane, or they are as strong. In other words, you want to put in is it can be also be as weak. Okay, either way it is fine. Okay, so now we have figured out the optimum ratio already. Okay, so we have done the ratio A to B. The next one is we're going to design the most efficient cross section. So we are given the numbers now. Okay, so I'll write down the numbers. Okay, so what we are given is the length. Okay, the length is equal to 20 inch. The Young's modulus is equal to 10.1 times 10 to the power 6 psi. And then we have the load given P is equal to 5 times 3 pounds. And the factor of safety is equal to 2.5. Okay. Right. So what are the formulas, or what are the formulas that we are going to use? Okay. So we are given that factor of safety is equal to P critical over P, right? So we have to determine our P critical. So therefore, our P critical is equal to 2.5, and the load is 5 times 10 to the power 3. So this is equal to 2.5 times 5 power 3 is equal to 12.5 times 10 to the power 3 pounds. Okay, so we know that. So we are going to design based on the optimum area, right? So the critical stress that we're going to have. So if we come up with our critical stress. Now, why we need to use critical stress? Why am I introducing critical stress? Because now we know that we have our critical load divided by A, and this will be equal to pi squared E over our equivalent length divided by radius of gyration squared. So this is the general formula that we like to use. Okay, so this is the general formula that we're going to use. Now we have to be careful over here. Okay, we have to be careful. What do I mean to be careful? Is we have to know. So as I said, this is the general formula. Okay, we have to be careful is because the R over here can either be RZ. So hold on, is it RZ? I can't remember. Can be RZ or RY. Okay, so we have to be cautious. Okay, so now we know that area is going to be the same. Okay, so let's calculate. Let's see what we need. So we need to determine our area. Okay, so area is the same whether you consider XY plane or YX plane. So let's just do the area first. So area A is equal to A multiplied by B. Okay, so let's say we substitute the condition. Okay, we're going to use A is equal to 0.35B. Okay, we're going to use A is equal to